Tensions around the public role of science arise partly from the belief that the cultural credibility of expertise rests on communicating in terms of consensus. But while in science new knowledge is expected to challenge current consensus, the public sees scientific credibility strained.
Many people seem unconvinced that we're warming our planet through the emission of greenhouse gases.
Are you saying the whole community, or a majority of the community of climate scientists, are skewing their data? Is that what you're claiming?
Scientists have been manipulating evidence.
Evidence is unequivocal. There's no doubt about it.
It's a subject that polarizes opinion. Not surprisingly, since climate science affects so many elements of our lives, from politics to economics to how we live. With so much at stake, scientists are rightly held to account. It's not just a clash of ideas, but whether people actually trust science. And trust in other scientific theories has also been eroded, such as the safety of vaccines. There have been angry protests against the use of genetically modified foods.
It's time for us to say, no, we don't want it. We don't want that new technology.
Are the public right not to trust science? Or is there something else that's not working?
Science's potential to empower lies in participatory practices that encourage shared knowledge, collaboration and shared ownership. The relationship between science and the public does not need to be one of blind trust. Scientists are not and should not be seen as modern priests, experts who pronounce on all manner of things with scientific knowledge as the ultimate authority. Contrary to popular depictions of science, science does not rely on authority as an indicator of truth. Results should always be subject to challenge from experiment. Science is liberating if it produces knowledge that empowers people to challenge dogma and beliefs. Policy making requires public participation and engagement. For this, the public needs to be able to understand, be informed and be given access to all the evidence. Messages of apocalyptic peril and emotional appeals might be effective in addressing public apathy and inspiring change, but could also engender distrust or disenchantment, and deliver short-lived results.
When we're growing up, we tend to be pretty credulous. We just believe almost anything that people tell us, especially authorities and adults and textbooks and politicians and television, YouTube, the internet. I mean, there's just this sort of sea of information coming at us. And how can you tell the difference between, it's right or it's wrong? How do you know? People believe weird things because our brains are wired up to find meaningful patterns. You think if you see the face in the cloud or the face on Mars or the Virgin Mary in a grilled cheese sandwich or on the side of a window. Many patterns are real, and it's good to know what those patterns are, and that's called learning. We connect A to B, and often A really is connected to B. Problem is, a lot of patterns are false. They're superstitious thinking. They aren't real. I'm often asked when I give talks, why should we believe you skeptics? And my answer is, you shouldn't. You shouldn't believe anybody based on authority or whatever position they might have. You should check it out yourself. And we call this generally our baloney detection kit, sort of inspired by Carl Sagan's idea that there's a lot of baloney out there and we need a kit to detect it. And that kit is called science, and that's what science does best.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it. Now you see, of course, that with this method we can disprove any definite theory. If you have a definite theory, a real guess from which you can really compute consequences which could be compared to experiment, then in principle we can get rid of any theory. We can always prove any definite theory wrong. Notice, however, we never prove it right. Suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simply not proved wrong. Because in the future, there could be a wider range of experiments, you could compute a wider range of consequences, and you may discover then that the thing is wrong. The theory had been failed to be proved wrong and could be taken to be temporarily right, but it can never be proved right because tomorrow's experiment may succeed in proving what you thought was right wrong.
Asimov was a great writer of fiction and non-fiction, science and science fiction. He received a letter from a non-scientist who wanted to correct his attitude about science. I'll quote him. "Every century, people have thought they understood the universe at last, and in every century they were proved to be wrong. It follows that the one thing we can say about our modern knowledge is that it is wrong." My answer to him was, "John, when people thought the earth was flat, they were wrong. When people thought the earth was spherical, they were wrong. But if you think that thinking the earth is spherical is just as wrong as thinking the earth is flat, then your view is wronger than both of them put together." The basic trouble, you see, is that people think that right and wrong are absolute, that everything that isn't perfectly and completely right is totally and equally wrong. Once people believed the earth was flat, and they were wrong, but they were also very nearly right. The curvature of a flat surface is 0, and the curvature of the Earth's surface is very nearly 0, to a certain level of approximation, the kind of measurements the ancients were capable of. After some rather brilliant observation by great scientists such as Aristotle, the basic idea of a spherical Earth was advanced, and measured a century later by the Greek philosopher Eratosthenes, by noting the difference in shadow lengths at different latitudes. We thought then that the Earth was a sphere, and that the actual curvature of the Earth must be 0.00126 per mile, a quantity very close to, but not quite equal to 0. This difference was important in our ability to make accurate maps and sail great distances without missing our destination. So then we thought the Earth was a sphere, but that was also wrong. Based on observations of the other planets, Newton showed that rotating masses are very slightly flattened at the poles. Scientists measuring the Earth very precisely, using newer instruments, were able to determine the degree of oblateness, the measure of departure from a true sphere. The correction in going from spherical to oblate spheroidal is much smaller than going from flat to spherical. Therefore, although the notion of the Earth as a sphere is wrong, strictly speaking, it is not as wrong as the notion that the Earth is flat. What actually happens is that once scientists get hold of a good concept, they gradually refine and extend it with greater and greater subtlety as their instruments of measurement improve. Theories are not so much wrong as incomplete.
I'm going to give you guys 3 numbers, a 3-number sequence, and I have a rule in mind that these 3 numbers obey. And I want you to try to figure out what that rule is. But the way that you can get information is by proposing your own set of 3 numbers, to which I will say, yes, that follows my rule, or no, it doesn't follow my rule, and then you can propose what you think the rule is. Is that fair?
Yeah.
Yeah, okay, so here are the 3 numbers. 2, 4, 8.
2, 4, 8.
You don't need to continue the sequence, you can propose a totally different sequence, whatever you want to propose, and I will simply say yes or no, that follows my rule.
2, 4, 8. 16, 32.
16, 32, and
64.
Yeah. Those also follow my rule.
Okay.
What's the rule? What do you think?
Multiply by 2.
That is not my rule.
What?
That's not my rule. But you're allowed, if you want, propose 3 other numbers.
3, 6, 12.
3, 6, 12.
3, 6, 12 follows my rule.
10, 20, 40.
10, 20, 40.
That follows the rule.
Yeah, I'm still multiplying by 2.
I know. I know what you're doing. And yes, it follows my rule, but no, it's not my rule.
5, 10.
10 and 20.
Follows my rule.
100.
200. 400.
Follows my rule.
500, 1,000, 2,000.
Follows my rule.
Want me to keep going?
But do I just keep going? You're going to tell me your rule?
Am I doing it the wrong way? Am I approaching this the wrong way?
You're totally fine,
okay.
But you're approaching it the way most people approach it. Like, think strategically about this. You want information.
Yeah.
I have information. The point of the 3 numbers, right, is to allow you to figure out what the rule is.
Okay.
Okay, I'm going to give you the numbers that I don't think fits the sequence and then see what you say. So I'll say 2, 4, 7.
Fits my rule.
So whatever I propose is right?
So is your rule like you can propose any number?
So the rule is anything we say is yes.
No.
Damn it.
But you are on the right track now. Hit me with 3 numbers.
3, 6, 9.
Follows my rule.
Oh, that didn't follow my rule.
This is good, right?
5, 10, 15.
That follows my rule.
What? Oh. Really?
Yeah.
I don't believe this.
1, 2, 3.
1, 2, 3.
Follows the rule.
What about 7, 8, 9?
Follows. Yes, that follows the rule.
8, 16, 39.
Fits the rule.
Excellent.
But we're no closer to the rule. I want you to get to the rule. How about 1, 7, 13? Follows the rule.
What?
11, 12, 13.
How does this
follows
make
the rule.
sense?
10,
I don't
9,
know how
8.
to do this.
Does not follow the rule. 10, 9, 8 does not.
Oh, so is it all in ascending order?
Booyah.
Okay.
Up top. Yes, first
that
ones
what it
to get
is?
it. You guys nailed it. That's the rule. That's
so
the rule. Increase numbers in increasing order.
Aw.
Numbers in ascending order.
Oh, so much
1, 2, 3, 4, 5, 6, 10, 15, 25. Doesn't matter. Any numbers in ascending order. What was interesting for me was that everyone I spoke to came up with a rule very early on and then only proposed numbers that fit with that rule they were thinking. I was looking for you guys to propose a set of numbers that didn't follow your rule and didn't follow my rule. I was looking for you guys not to try to confirm what you believe. You're always asking something where you expect the answer to be yes, right? Like you're trying to get at it. Yeah.
But instead you want to get the no.
You want to get the no because that's much more informational for you than the yes. Like if everything's
No, that
giving a
is
yes.
true. That is really true once you say that.
The point is you can never prove a theory true, and that is what's so important about the scientific method. We set out to disprove our theories, and it's when we can't disprove them that we say this must be getting at something really true about our reality.
So science has a critical role, empowering the public to not simply accept, but to understand and engage in the process of change.
Science is often seen as a difficult subject, and yes, it is, because it's detailed, meticulous, and demands the highest possible accuracy. But those qualities also make it very easy to check. There's a mechanism for documenting facts that has survived for 200 years and has given us all the technological achievements we enjoy today.
Peer review is very important to make science credible. The authority science can claim comes from evidence and experiment, and an attitude of mind that seeks to test its theories to destruction.
We measure scientific progress in our ability to reduce the uncertainties, and by that measure we're making extraordinary progress.
But there may be a problem in the way those uncertainties are communicated to the public. Scientists may not be willing enough to publicly discuss the uncertainties in their science, or to fully engage with those that disagree with them, and this has helped polarize the debate. Searches on the internet do not differentiate between thoroughly researched evidence and unsourced, uncorroborated assertion. Conspiracy theories compete on level terms with peer-reviewed science.
Things are a little different when you have a denialist or an extreme skeptic. They're convinced that they know what's going on, and they only look for data that supports that position, and they're not really engaging in the scientific process.
Some extreme skeptics decide what to think first, and then cherry-pick the data to support their case. We scientists have to acknowledge we now operate in a world where point of view, not peer review, holds sway.
The goal here is not to make everybody a scientist. That's not the goal. What a boring world that would be. You want artists, you want musicians, you want novelists, poets. You want the rest of this. What matters is whether they're scientifically literate and maintain that literacy and that curiosity throughout their lives, no matter what becomes their profession. Most important feature is the analysis of information that comes your way. How do interpret information that comes to you, how to think about what somebody says, how to judge what it is that someone else says, judge the likelihood of it being correct or not. No longer can you invoke common sense to judge whether or not that's accurate, whether or not it's true, because all that matters is that it's measured to be true. Period.
Science isn't just about knowing stuff. Science is a way of thinking. It's about how you look at the world. Science is questioning what people tell you, even your teachers. Studying science develops a wide set of transferable skills. You learn to approach problems in an organised way and work out creative ways of solving them. You learn how to get things wrong and analyse why. How to be open-minded about new or alternative ideas that challenge your thinking. And how to have the courage to change your mind and try again.
A model is a representation of an object or process that describes and explains phenomenon when it can't be experienced directly. In science, we come up with lots of rules and laws to describe the world. A simulation is the recreation of a real-world process in a controlled environment. It uses modeling to figure out the result of the simulation.
In the most broad definition of the word, modeling could be said to be showing an example of a scenario. When a model is on the runway, he or she is showing an example of what the clothing would look like on a person. Many people enjoy building model cars or planes. Again, these models give an example of what real cars and airplanes look like. Mathematical modeling refers to the creation of mathematical formulas to represent a real-world problem in mathematical terms. You probably are already aware of some very well-known mathematical models, those that give perimeter and area of a square. The models are simply the formulas. P equals 2L plus 2W, and A equals L times W. P is perimeter and A is area. L means length and W means width. So yes, these formulas are mathematical models because they are examples or representations of the image that can be used repeatedly with different values to obtain different results for the same scenario.
We have a strong understanding of how the universe works, and a lot of that comes down to the ways that humans think, largely because of something called abstraction. An abstraction occurs when we take something real and represent it in a different, often simpler form. Let's say that you're sitting in math class and begin learning algebra. Suddenly, instead of just numbers, you're doing math with letters. You multiply variable x by variable y and get variable z. These letters represent numbers. This is an example of abstraction, substituting something real with something that represents it in a simpler way. When we use one thing to represent another, it can be easier to understand, and that's the basis of a conceptual model, a way of representing a particular concept, or set of concepts, that helps people understand or simulate the subject of that model. Often drawn as diagrams, conceptual models show relationships between factors and the flow of data or processes.
Have you ever wondered why, when we look around us in the natural world, we see very few straight lines? But the straight line is ubiquitous in the systems we engineer. From buildings to circuit boards, it appears to be the default position. One way to understand this is that the systems we engineer are based upon our scientific and mathematical understanding of the world, which has inevitably started by describing the simplest and most orderly systems, that is to say, those that are composed of linear forms and relations. From Euclid to Newton and on, science has been focused upon the orderly systems of perfect squares, triangles, and linear relations of cause and effect that can be encoded in beautifully compact equations. Thus we describe the real world as a kind of approximation to these perfect linear forms. But linear is basically a fancy word for line, and a line is often understood as the shortest or most direct path from one point to another. To say there is a linear relationship between two things is to say that there is a direct relationship of cause and effect between them. There are of course many examples of linear systems, particularly within physics, but we can capture the underlying logic of linear systems in general with a model that has only two simple rules called the superposition principles, which states firstly that the output to the system will always be directly proportional to the input. So if there's a linear relationship between the amount of fuel I put in my car and how far it will go, well then if I put twice as much fuel in the car, it will go twice as far. And secondly, that if we add two or more systems together, then the output to this combined system will simply be the sum of the two outputs of the original systems. So say we have two tractor factories, each producing 1 million tractors a year. Well, if we merge them, then we will get a factory that will produce 2 million tractors a year. Linear systems are deterministic, meaning that if we know their present state, we can fully determine their past and future states. This can be seen by plotting a linear system as a graph, where it will always be depicted as a straight line. Although linear systems modeling has proven highly successful in many areas and is often a very good approximation, the reality is that we live in a world with ecosystems, economies, societies, and physical systems that are not governed by the superposition principles and thus are what we call non-linear. An example of non-linearity might be listening to two of your favorite pieces of music at the same time. Because there is a relationship of interference between them, the result of the experience will not be a simple equation of adding the enjoyment from listening to each independently. This illustrates how non-linearity arises whenever there is some relationship between elements within the system that can be either synergistic, making the output of the system greater than the sum of its parts, or one of interference, making the output less than the sum of its individual components. To illustrate this further, let's take an example of 4 workers producing clothing. In isolation, each seamstress can sew a given amount of clothes within a day. Now if we put them together, we might get one of 3 results. Firstly, they might not interact with each other very much, meaning the whole would simply be the sum of its individual parts. But equally likely, they might form some cooperative relationship which lets them each specialize in a particular function, making them more efficient as a whole, and thus the output of the system would be greater than the sum of its parts, due to these synergistic relations. Or inversely, they might start all talking with each other, getting little work done, and thus the total output would be less than the sum of the individual outputs due to these relations of interference. Non-linearity can also arise from feedback loops, whereby the same process is iterated with the output fed back as the input to the next cycle. A classical example of this is compound interest, where at the end of each period the balance plus interest is fed back into the formula to compute the next cycle of interest accumulation. Iterative functions are an important concept within nonlinear science, and have been used to create a whole new type of geometry called fractal geometry, whereby iterating a simple function generates irregular, organic-looking patterns that can model many of the geometric forms we see in nature, from the structure of seashells to the rugged formation of mountains. In these nonlinear systems, superposition fails, meaning one cannot break the system down into smaller sub-problems and then add their solutions. We must consider a nonlinear problem in total. It is this need to approach nonlinear systems as a whole that is giving rise to new, more holistic approaches to science that are developing under the canopy of the term complex system science. Nonlinearity, in all its shapes and forms, is at the heart of many of the 21st century challenges to science, as we try to extend the scientific framework beyond its dependency upon linear systems theory to finding new ways to embrace the complex world we live in on its own irregular and imperfect terms.
Defining environmental.
Rather, as the car became a dominant means of transport, the car develops interdependencies with social, technical and institutional factors including production and supply chain systems, car users, regulation and infrastructure and culture, creating a system called a socio-technological regime. The factors and their interdependencies in this regime over time lock society into the dominant technological solution. So, how does this happen? First, as a technology like the car matures, people working in the industry, the Car designers, research managers, engineers and so forth tend to develop common assumptions, knowledge, beliefs and habits about what are possible and legitimate transport solutions. Second, car manufacturers and their suppliers will try to protect their investments and market share. The economies of scale that have developed in producing cars also prevents new transport technologies competing with them. Third, financial investors and insurers of technologies are often sceptical of new technologies, making it difficult for innovators to get financial capital. And in New Zealand, this is particularly so for the commercialisation stage of new innovations. Fourth, the built environment such as suburbs and roads have co-evolved with a private car. Oil was cheap up to the early 1970s, which led to major motorway expansions and the creation of suburbia around many cities, and today most of us rely on private cars to drive to work and get around. As the built environment is long-lived and expensive to change, we get locked into a dependency on private motorised cars. Fifth, our lifestyles and attitudes co-evolve with the evolution of the car as the dominant means of transport. We've got used to driving where and whenever we want and expect to continue to do so, and this influences which transport technologies are seen as socially acceptable. We have collectively created symbolic associations with the car, reinforced by media and popular culture. For example, cars are symbols of individual freedom and successes, while wearing lycra and riding a bike is not. Finally, even when we want to switch to another transport option, we develop habits and routines connected to our cars which we find hard to break. And then there's public policies such as taxation and regulation which also co-evolve with the dominant technology, often creating an uneven playing field for other technologies to compete. In New Zealand, policy has privileged motorised cars by not charging drivers all transport externalities. For example, the public cost of vehicle-related water and air pollution and carbon dioxide emissions. So, a new transport technology does not just have to compete with the car, but it has to compete with the whole system of social, physical and institutional factors that have co-evolved with the car. And this tends to lock society into this technology trajectory even when it has become suboptimal. So, how do radical technological innovations succeed? Well, first, the current transport system has to be disrupted. Pressures and events at what MLP refers to as the landscape level occur and put pressure on the current system or regime. Pressures may include changes to society's dominant values and beliefs, and events such as wars and natural disasters. For example, growing concern over climate change has gradually pushed climate change onto political agendas, raising consumer concern and creating policies which collectively disrupt the car's symbolic and financial position. These landscape disruptions create windows of opportunity for new and radical innovations to gain market share. Radical innovations are often referred to as technological niches which develop in protected spaces within the regime. But if a niche is not mature enough when a window opens, it won't be able to take advantage of it. Timing is critical. If the niche is mature enough, then it may either replace the regime by competing with it, for example electric public transport, or be subsumed into the regime as a means of reducing the landscape pressure, for example hybrid cars. This latter adoption, however, might over time push the incumbent regime trajectory in a new direction, for example further stimulating electric vehicle development. When we develop a richer understanding of how social and technological change occurs, we can stimulate new ideas to create change for a sustainable future, for government policy, for business practice and innovation, and for communities.
Intervening in the social ecological systems without understanding them can hamper impact and even result in unintended negative consequences. It is important to understand what a system is and how it functions. Broadly speaking, systems are complex sets of nested relationships between elements, which may include societal actors, ecological agents and socio-ecological issues. Systems thinking and facilitate a shared understanding of complex problems and aid in designing pathways for interventions. When approached in a reflective, collaborative, inclusive and learning mode, systems thinking and facilitate a collective understanding of complex problems and guide strategic decision-making.
The term paradigm shift was coined by Kuhn, 1962, referring to the shift in science from Newtonian to Einsteinian physics. Kuhn's work has since been extensively used to capture system transitions, with Hall, 1993, for example, using the concept to explore the transition from a Keynesian economic paradigm to a monetarist one. Paradigm shift, according to both Kuhn and Hall, happens when the anomalies and shortcomings of the current paradigm are repeatedly pointed out. Proponents of the new paradigm speak loudly and with assurance about it, and are placed into positions of visibility and power. And energy is focused on converting those people who are likely to be open-minded to the change.
We must recognize that what we perceive is not reality itself, but rather a carefully crafted narrative being presented to us. Our brains work hard to bend reality to meet our prior experiences, our emotions, and our discomfort with uncertainty. They are masters of adaptation, constantly striving to make sense of the world around us in a way that aligns with our existing knowledge and beliefs. Think about how our brains fill in the gaps when we encounter incomplete or ambiguous information. When faced with a blurry image or a fragment of a conversation, our minds effortlessly piece together the missing details, drawing from our past experiences and expectations. We create a coherent narrative, filling in the blanks to make sense of the situation at hand. Emotions also play a significant role in shaping our perception of reality. Our emotional states can color our experiences, influencing what we pay attention to and how we interpret events. A gloomy mood may cast a shadow over even the brightest moments, while a joyful disposition can enhance our appreciation of the world's beauty. And then there's our inherent discomfort with uncertainty. Humans have a deep-seated need for certainty and predictability. We seek patterns, impose order, and create explanations to alleviate the anxiety that arises from the unknown. Our brains strive to reduce ambiguity, often resorting to simplifications and stereotypes to make the world feel more familiar and manageable. But this constant bending of reality comes with its limitations. Our brains can inadvertently lead us astray, creating biases and distortions that skew our perception. We may selectively attend to information that confirms our preconceived notions, ignoring contradictory evidence. We may fall prey to cognitive biases, such as the confirmation bias or the availability heuristic, which can cloud our judgment and lead us to faulty conclusions. Recognizing these tendencies is crucial for navigating the complexities of our everyday lives. It reminds us to approach information with a healthy dose of skepticism, to question our own assumptions and biases, and to seek out diverse perspectives. In a world filled with uncertainties and diverse viewpoints, it becomes imperative to cultivate intellectual humility and open-mindedness. Let us challenge our own biases, question the narratives we encounter, and engage in thoughtful dialogue with others. We must approach the quest for knowledge with curiosity, embracing the vastness of possibilities and the richness of differing perspectives.
How do you look at the world? What does the world look like through your lens? If you're scientifically literate, the world looks very different to you. It's not just a lot of mysterious things happening. There's a lot we understand out there. And that understanding empowers you to, first, not be taken advantage of by others who do understand it. And second, there are issues that confront society that have science as their foundation.
That influences your health, your safety, how you're going to have to vote, what issues are before you politically.
If you're not scientifically literate, it's in a way you are disenfranchising yourself from the democratic process, and you don't even know it.